Hi, this is an introduction to our latest work, Fumos, Neural Compressions and Progressive Refinement for Continuous Point Cloud Video Streaming. Point cloud is a set of 3D points, and each point is defined by geometry parts XYZ and color parts RGB or YUV. There are also other attributes like reflectance, transparency, and etc. It supports such degree of freedom interaction, which is very important in VR application. Point cloud video, denoted as PCV, is a dynamic visualization of point cloud data captured over time. There are many networking challenges of PCV. We introduce two main challenges here. First, volume of data is too large for transmission in real time, which greatly exceeds the common bandwidth capabilities of commodity devices. Secondly, inaccurate FOV prediction results in poor video quality. Many existing works, including ours, adopt FOV prediction to reduce the data transmission, thereby significantly reducing bandwidth consumption. However, Figure 2 shows that prediction accuracy decreases sharply with large windows, and Figure 3 indicates that the limited time for downloading small prediction windows significantly decreases the video quality. We observe that the neural codec have a high compression rate but a low decoding speed, whereas all-tree-based codec have high decoding speed but lower compression rates. Given that we design a progressive refinement framework, the client could download most of the video data compressed by the neural codec using a very small amount of bandwidth. Since neural codec is not FOV adapted, the client could prefetch low-quality PCV encoded by neural codec at long prediction window. For the short prediction window, we could request the PCV within the predicted FOV to refine the video quality. We also observe that the interframe codec separates the frames into key frames and predicted frames. The key frame decoding is much more time-consuming than that of the predicted frames, because predicted frames are based on differences relative to agent frames. Given that the decoding of keyframe within each chunk could run simultaneously, and the predicted frames could decode quickly afterwards. Given the observations and motivations, we design Fumos, a novel system that preserves interactive experience by avoiding playback stalls while maintaining a high perceptual quality and high compression rates. This is the system overview of Fumos. We consider a video on-demand scenario. PCV is prepared in the edge server. The PCV is split into many video chunks. For each chunk, it is first encoded by all-tree data structure. We control the fidelity and data size by the hyperparameter level of depth. The larger LOD is, the more details will be preserved. Then we adaptively allocate the workload for different codec. We design NPCC, which through the interframe feature learning to achieve high compression capability. Let's see more details about NPCC. We use the multi-scale encoder to generate the high-dimensional feature for each frame of point cloud. The multi-scale encoder consists of two basic encoders, which is constructed by 3 downsampling blocks. We use sparse convolution to downsample point cloud and then design a density learning module to learn the density feature from diminishing points. We then aggregate the multi-scale feature into merged feature and forward it to sparse convolution to generate the final feature. We derive the feature of 2 consecutive frames and then forward them into motion estimation parts. The motion estimation module will produce the motion vector between 2 consecutive frames. Then motion compensation module compensates the motion to the previous frame to generate the subsequent one. As we have the predicted feature for current frame YT and motion vector VT and residual RT, we forward these features into deep entropy model. The deep entropy model consists of deep neural network that for gauging the entropy of data targeted for compression, and then algorithmic encoder and algorithmic decoder will be utilized to compress and decompress the data adhering to the entropy values. We also design FOV adaptive codec, which is much faster but lower in compression rates than MPCC. The FOV adaptive codec learns over historical FOV traces and PCB contents to predict future FOV. We input unhistorical FOV traces to get a cos FOV delta ST. We generate historical quantum feature FT-1 and the current feature FT. We merge these two features to refinement the cos FOV delta ST into a accurate FOV bar ST. The data is transmitted and subsequently decoded at the terminal. The network conditions and latency are collected as sensitive for future optimization. We also utilize Lyapunov optimization to adaptively control the hyperparameters based on the network conditions and previous states to maximize the overall QoE. Here is an illustration of progressive refinement process. MPCC is used to generate the base layer, and then FOV adaptive codec generates the enhanced layer. We merge these two layers to output a final layer. We can find that the error within the FOV remains high perceptual quality. Here are some more experimental results. This is the figure of performance comparisons of various codecs using overall QoE. Fumos improved QoE by more than 87.5% compared to the baseline methods. This figure shows the performance comparison of codec using rate distortion curve. It indicates that MPCC is much better than that of GPCC and VPCC in terms of the BD rate scans. This figure shows the normalized QoE under fixed gamma and LD without Lyapunov optimization. The normalized value obtained by the Fumos equals to 1. The finding shows that the Lyapunov optimization strategy is very effective. This table shows the performance metrics of methods across datasets. It indicates that Fumos decodes over 260 times faster than Jaco. In the AI datasets, throughput is reduced by 92.8% and 51.3% from Jaco and GPCC, but only with minor jobs of D1 PSNR. We also carry out the ablation study. This table shows that the density learning helps improve reconstruction quality in MPCC. And utilizing the downsampler or tree or FOV filter boosts the default decoding efficiency while not degrading visual quality significantly. More details, please refer to our paper. Thank you.